Welcome back. So this is lecture 17 in this course on Bayesian modeling. The topic of today's lecture is likelihood, prior and posterior distributions and how we can compute them in R. Okay. So in the previous lecture, we have seen how do we use Bayes theorem for statistical inference. Particularly, we saw how do we do parameter estimation in the Bayesian framework. So given any data from any experiment, we make some assumption that the data might come from some probability density function, let's say f of x theta, right? Now, given that data and given that assumption, our goal is to estimate that what value of the parameter, what value of theta might have generated the data. Okay, so that's parameter estimation. We do this process every time whenever we are doing any statistical inference. Now, in Bayesian framework, we do not want to estimate just a point value of the parameter, but we want to estimate what is the true distribution of the parameter theta. Okay, because we want to also estimate the uncertainty around that true value of the parameter, right? And that's what we call the posterior distribution in the Bayesian framework. And there is a way to estimate posterior distribution of any parameter given the data. So to say it more generically, so let's say you have some data x which comes from an underlying probability density function. This is your assumption, right? So you assume that your data x comes from the underlying probability density function f of x theta, right? Now, posterior distribution of the parameter theta given the data. So you can call it, this is the probability distribution. This is the true distribution of parameter theta conditional on this observed data. Okay, that's what we want to estimate. That after seeing the data, what do I know about the true distribution of theta? Okay, this is given by likelihood of theta given the data. So after seeing the data, you can compute the likelihood function. So this is the likelihood function. So likelihood of any value of theta given the data, prior density of theta. You can call it posterior distribution of theta if you're talking about the whole distribution. So prior distribution of theta. So this is the true distribution of theta that you know before seeing any data, right? So this is the information you have about this parameter before seeing any data. Okay, so let's say before seeing the data, you think or you believe, or from previous studies, you know that theta is somewhere between 0.7 and 1. Okay, and you can express that as a distribution, that assumption as a distribution. So that's your prior distribution. Okay, so this is what you know about true value of theta before seeing any data, and this thing is divided by marginal likelihood, which is just a likelihood into prior, integration of likelihood into prior with respect to theta. Okay, so this is how you use Bayes theorem to estimate a distribution of true values of theta. So what is the range of true values of theta, which values of theta are more likely, which value of theta are less likely given the data. So you want to estimate the distribution of parameter theta, true distribution of theta given the data after seeing the data. Okay, so this is called the posterior distribution. We call it the posterior distribution. Okay, so this is posterior distribution of theta. This is called the likelihood function. This is the prior distribution of theta, and this is the marginal likelihood. Okay, so this is what we discussed in the previous lecture. Now let us take an example to see how we can compute all these terms. So how do we compute likelihood function and prior distribution and the posterior distribution? Okay, so we'll take a simple example and see how it works in practice. Okay, so let us say you are doing an experiment where participants have to recognize whether the string shown on the screen, so they will see a string on a screen one by one, and they have to decide whether the string they are seeing on the screen is a proper word or a meaningless non-word, right? So in this case, it does not make any sense. This string is not a meaningful word in English, so they have to respond no, for example, here. Versus if they see a book on the screen, they will have to respond with yes. So they are given two options. They would respond with either yes or no, right? Seeing the whatever the string is there on the screen. So they need to recognize whether the string on the screen is a word or a non-word. So they need to recognize this, right? So this is a recognition task, word recognition task. Okay. Now let's say a participant is tested on 50 trials, basically 50 strings. Okay, so you are presenting 50 strings one by one to a participant, and then this participant has to, every time he has to recognize whether it is a meaningful word or not. Okay, so the task of the participant is to recognize whether it's a word or not word. Okay, so let us say they are given 50 trials, okay, 50 strings in this experiment. Okay, what we are interested in is this, that how many times they produce a correct response. Okay, how many times they produce a correct response. So maybe you can have hypothesis about, let's say, they would produce a correct response more than 50% of the times, right? So you can have a hypothesis like that. We are not going into hypothesis for now, but let's say this is what you are interested in modeling. We will just talk about modeling for now. So you are interested in modeling that how many times they produce a correct response. So that's the outcome of your experiment, right? And this could have a value between 0 and 50. So let's say they produce a correct response all 50 times, or let's say 0 times, or the 10 times, or 20 times. Okay, so that's the number, right? So the variable that you want to model is the number of correct responses, which can be anywhere between 0 and 50. Okay. Now, in order to model this variable, number of correct responses, so think of this as your random variable, right? You need to now make some assumptions, right? And we talked about this in the previous lecture. So this is the first step of inference. So this is step 1, that you need to make some assumptions. Okay, and actually you make two assumptions in the Bayesian framework. First is called the likelihood assumption. This is basically your assumption about the underlying generative process behind your outcome. So the number of correct response you would observe in an experiment, there should be an underlying generative process that is producing n number of correct responses in a particular experiment. Okay, what can you assume here? What could be the underlying probability distribution behind number of correct responses that you would see in an experiment? Well, one reasonable assumption would be this. You can make a different assumption as well, but in this case, a very reasonable assumption would be this, that number of observed correct responses comes from a binomial distribution, right? With underlying probability of success, underlying probability of producing a correct response in a particular trial being theta. Okay, so theta is the underlying probability of producing a correct response in the IIT trials. You can also write it like this. So theta is underlying probability of correct response in the IIT trial, right? And this is theta. Another second kind of assumption that you need is your prior assumption about the parameter, right? You can call it prior assumption about theta. So what are the parameters here? You have only one parameter, theta. So what is your prior assumption about this parameter theta? Okay, so what do you think are likely values of theta? What do you think is the distribution of true values of theta, right? So let us say I believe that, or from previous studies or from my own experience of this kind of study, I know that whenever participants do a word recognition task, they are accurate, let's say 85% of the times with some variability. So in some tasks they are not very good, so there is some variability, let's say between 0.6 and 1, or 0.6 and 9 or something like that, but they are accurate, let's say 85% of the times. Okay, so accordingly you can have a prior distribution around theta. Okay, so for example in this case you can assume a normal distribution, or even a better reasonable prior distribution here could be beta distribution, Why beta? Remember, theta can have values between 0 and 1. It's a probability parameter, right? So it's probability. So it need to have values between 0 and 1, and beta is exactly the distribution that gives you continuous values between 0 and 1, right? And you want to express that value of theta is somewhere around 0.85. So you can set up your parameters accordingly. So let's say I do it like this. Beta with first shape 1 parameter 85, shape 2 parameter 15. Okay. This would give me a reasonable prior distribution around theta. Okay. So this is fine. So far I have likelihood and prior assumption about theta. Okay. So my assumptions are all in place. Okay. What is the next thing I need to do? Now I need to, of course, collect data. Right. So now I need data for further inference. So far I have only assumptions. So let's say now you have collected the data and you observe that the number of correct responses in your experiment is actually 45. Okay. So that's your observation. Okay. Now what we do with this? With this observation, what you can do is you can actually compute your likelihood function. What is the likelihood function? Likelihood function is L theta given your data. So in this case, number of correct responses. Okay. And basically you just need to plug in values of theta, different values of theta, and the number of correct responses, which is fixed, right? So the data is fixed now. Okay. So this is exactly in the same way how we compute likelihood function in any other case, right? So what we do to compute the likelihood function? Basically what you can do is this, that theta, you can take a lot of values of theta between 0 and 1. Okay. So let us say you take 1000 values of theta or 10,000 values of theta between 0 and 1. Okay. So let me call those values theta 1, theta 2, theta 3, theta n, but it should be huge number. Okay. Then for each value of theta, you can estimate the likelihood. Now you have each point value of theta. For each point value of theta, you can calculate the likelihood given the data, which is number of correct response 45, because you just need to plug this in into the formula of binomial distribution, because that's what will give you the likelihood for any particular value of theta. So likelihood function is n chooses x. Now x is 45 here. That's the number of correct responses. Theta I to the power 45, 1 minus theta I to the power 5, right? So this is how you can calculate likelihood for each theta I. And once you get likelihood values and likelihood values corresponding to each theta I, then you can draw its plot, right? So that would be your likelihood function. Okay. So this is, let me call it step 3. So this is estimation of likelihood function. Once you have the likelihood function, now you can estimate the posterior distribution. So posterior distribution of theta. Okay. How do I estimate posterior distribution? So what was Bayes' theorem? Posterior distribution of theta given some data x is given by likelihood into prior divided by marginal likelihood. Okay. So that was posterior distribution of theta. How do I calculate this? So one thing I need to do is, so let us go with the same vector of theta, which you have used here to compute the likelihood functions. Theta 1, theta 2, theta 3. So these are 10,000 values of theta between 0 and 1. Okay. Now for each value of theta, you have computed likelihood. Now for each value of theta, you can also compute its prior density. So what is the prior density of theta 1? What is prior density of theta 2? You can compute all this from the prior distribution of theta, right? From beta, whatever we chose, beta 85, 15, right? Okay. So this will give you likelihood into prior. Now you can divide this whole thing. You need to divide it by integration of this, right? Now integration in some cases, it would be possible to do this integration. So once you know the likelihood function and prior distribution, in some cases it would be possible to integrate, right? But in most cases it would be basically the function cannot be integrated at all, right? So you cannot find a proper analytical solution for the marginal likelihood, right? So what we are going to do, we are going to approximate this marginal likelihood. How can we approximate? If you just take the average, okay, if we take the average of all likelihood into prior from I is equals to 1 to n, this would give you an approximate marginal likelihood. This would give a good enough approximation, especially when you have fewer parameters and you have taken large number of samples. So if n is large, right? So you can do this. I will explain the logic why we are doing this later on. But for now you can do this. But idea you can understand here, because we are trying to calculate total probability of x, right? So for which what we do is that we sum this term across all mutually exclusive and exhaustive events theta 1, theta 2 and up to theta n, right? So we are doing the similar thing here. Okay, so this is fine. So this is basically a marginal likelihood, right? And this is likelihood into prior. So now we are computing this thing for each theta I, right? So what this is going to give you, posterior density for parameter value theta I, okay? So if you can compute it for theta 1, you can compute it for theta 2, theta 3 and so on. So basically you will get a vector of posterior densities, right? Now you can plot all these theta 1 to theta n on the x-axis. So basically all values of theta that you have taken on the x-axis and the corresponding posterior densities on the y-axis. Okay, corresponding posterior density on the y-axis. So you will get a posterior like this. Okay, that's it. So you have computed the posterior. So you just multiplied likelihood into prior, and then you divide it by some constant, which is basically marginal likelihood, which we approximated by taking average of likelihood into priors. Okay, let me show you how to do this in R. Okay, can we do all this process in R for the same example? Okay, so in order to do this in R, so what was our likelihood assumption? That number of correct responses, let me just call it n, comes from binomial underlying probability of correct response being theta. Prior assumption is this, that theta comes from beta 8515. Okay, now let us see, and the data you have is this, so let us call it x. So x is equals to 45 and total sample size is 50. So you have total 50 trials. Okay, so let us do this in R. Okay, so you have already written your assumption. So let us just start with how to compute likelihood, prior and posterior. Okay, so likelihood function first. So in order to compute likelihood, so data is now known and fixed. Okay, and number of sample size is also known and fixed. Only thing that is not known, or only thing that is a random variable now that will vary, is the parameter theta. So what we will do, we will create a vector of theta, a large vector of values, different values of theta. So one way to do this is to create a sequence of values of theta from 0 to 1, because theta can vary between 0 and 1. And how many samples we want to create? Let's say 10,000. Okay, so we have created 10,000 samples of theta between 0 and 1. You can see how they look like. Okay. This is theta. Fine. Now what we want to do, we want to calculate likelihood for each value of theta. Now what is our likelihood assumption? That data comes from a binomial distribution. So the to compute likelihood, you can use d binom function, because that's what will give you likelihood for corresponding values of theta. So in order to use d binom, you need to first pass on data. What is your data? X is 45, sample size is 50, and now probability, basically the theta vector is this theta. So this will give you a vector of likelihood corresponding to each value of theta. Okay, if you want to visualize it, you can actually visualize it using this function plot. Okay, so I'm plotting theta on x-axis and corresponding likelihood on y-axis, and this is how the likelihood looks like. You can see that this function peaks at 0.9 and most likely values are between, let's say, 0.7 and 1. Okay, so that's what the likelihood function tells us. What does the prior distribution tells us? So let us plot the prior distribution of theta. Okay, so for the same vector of theta, exactly same vector that we have used for computing the likelihood, for the same vector we can calculate prior densities, corresponding prior densities. So what was our prior assumption? That it comes from a beta distribution. So you can use d beta to compute prior densities. Okay, so we need to compute d beta for this whole vector of theta. Okay, that's what we are saying here, right? So theta comes from beta 85, 15, and then the shape parameters 85, 15. So this thing will give us prior densities corresponding to each value of theta. So you can see how these values look like, and let us plot them with theta. Oh, sorry, not likelihood, prior. So when I plot prior distribution of theta, this is how it looks like. So the distribution peaks at around 0.85 and the likely values are between again 0.7 and 0.95. So it restricts it to somewhere around 0.95. Okay, so that's the prior distribution, and they are slightly different. See, so this one peaks at 0.85, the other one peaks at around 0.9. Okay, so they contain different information. Your prior assumption about this parameter is different, and your data is telling you something different. So likelihood function contains the information which data tells you. Okay, so this is everything what data tells you. Prior distribution is your prior information before seeing any data. This is something that you already know before seeing the data. Okay, now we can compute the posterior, but before that you can try to approximate marginal likelihood. So let's say we approximate marginal likelihood by taking mean of likelihood into prior. Okay, this will give us some value of marginal likelihood, let's say 0.10. Okay, now we can go ahead and calculate the posterior distribution. Okay, so posterior would be likelihood into prior, because likelihood is now a vector of likelihood for each value of theta corresponding to vector of theta, and same is prior, and divided by marginal likelihood. Okay, so this should give us a vector containing posterior densities corresponding to each same vector of theta. Okay, so now you calculate the posterior. Now you can plot posterior densities with respect to theta vector. Okay, and this is how it looks like. So this is a graph of posterior. This is slightly different from the prior. So this is graph of posterior. This was graph of prior, right? So posterior is interestingly somewhere, so peaks at somewhere around 0.85 and 9. So it is between 0.85 and 0.9. Okay, and that would happen because you're multiplying likelihood and prior. So data tells you that the most likely value is around 0.9. Prior distribution tells you that the most likely prior value of theta is, let's say, 0.85. So a posterior would be somewhere in between. Okay, so we call it the posterior is a compromise between the prior and the likelihood. Exactly because the posterior uses both these information. It takes into account what was your prior assumption. It also takes into account what did we learn from the data. Okay, so likelihood is something that learns from the data. Prior is something that you believe or you know before seeing the data, and then we combine both these informations to get our posterior distribution. Okay, In the next lecture, we will see how to plot all these priors, likelihood, and posterior in a single plot using ggplot, so that we can easily visualize them. Okay, that would be a really cool way to basically visualize what was the likelihood, what was the prior, and how and what is the posterior. So we can compare them one by one. So what had changed from prior to posterior, right? So this is basically a simple code in R using which you can compute posterior distribution for simple cases. Now remember, this is a very simple case where you have basically one data point and you have only one parameter. Okay, so it was possible to do compute posterior in this way. Okay, but in most cases in practice this won't be possible because you'll have too many parameters, a complex likelihood, and also huge number of data sets. Okay, then we will need to rely on more advanced computational methods to compute the posterior distribution. Okay, but this is a good starting point to understand what is posterior and how we compute it for simple cases, right? So we'll take a couple more examples in the next lecture, and we'll see how we plot prior, posterior, and likelihood in a single ggplot, right? All right, so I will stop here for this lecture. We will meet in the next lecture to discuss more examples of estimating posterior distribution. All right, thank you.